Our first sort of inaugural speaker for this seminar series is Dr. Jiang, a longtime friend and colleague of mine now at the University of California, Davis. So Jiang got his PhD in 1995 from UC Berkeley, working with Peter Bickel in the statistics department. He then was on faculty at Case Western Reserve University in the stat department until 2001, and that's where we hooked up together and started doing some work together. In 2001, he left to go to UC Davis, and he's been a professor of statistics there since. He's very well known in a number of different areas of statistical modeling. So I wrote down a bunch of them here, but mixed effect modeling, generalized linear models, model selection, small area estimation, asymptotic theory, longitudinal data analysis, matrix algebra, numerical analysis. There's a variety of different things that he likes to fool around with. So, he is a fellow of the Institute of Mathematical Statistics. He's a fellow of the American Statistical Association. He's an associate editor for the Annals of Statistics, an associate editor for the Journal of Multivariate Analysis, and he's, I guess, the editor, coordinating editor for a new journal called the International Journal of Statistics and Management Systems. So, without further ado, I'd like to welcome Jiang. And
well, thank you very much for the very nice introduction. And this is the first time I've been in the city of Miami, although I've been in Florida a couple of times before. Of course, we all have heard about the Miami hurricanes, and I was just told that they have the season opener today. So I looked a little bit of search on over the internet and found this little website is currently ranked number 13 in the country. But this is just beginning of the season. You know, they used to win the national championships, so who knows what's going to happen at the end of the year. But anyway, wish them the best luck, and the national championships will be back soon. Okay. So, yeah, but actually, recently I've been paying much more attention to the University of Miami since my longtime collaborator and friend, Dr. Sunil Rao, moved to University of Miami. I noticed that the university now is one of the top 50 national universities. Congratulations on the move on the national rankings. And also the city of Miami is hosting the next year's joint statistical meetings. So that's a big event for statistics and also biostatistics, I guess. I don't quite remember we had any of the joint statistical meetings in Palo Alto or Berkeley, even though it's the top statistics department in the country. So it's certainly a big event. Well, here is the talk. Let me make it a full screen so we can view it a little bit better. It's a joint work of Dr. Rao and myself and one of my former students. This title is called Invisible Fence and Methods and Identification of Differentially Expressed Gene Sets. So I guess this term that fence is probably the one that catches your eyes, but I have to explain that a little bit so we know what the fence method is. So basically, it's a method that is recently developed for model selection. Okay, so later I'll try to build a connection between model selection and the gene sets identification problem. But right now, let's just think about fence as a method for model selection. Now here are a few more descriptions about this method. So what is the idea of fence method? Well, it involves a procedure to isolate a subgroup of what are known as correct models, of which the optimal model is a member. This isolation of the subgroup of model is accomplished by constructing a statistical fence or barrier to carefully eliminate incorrect models. So the name actually comes from here because this involves the construction of a statistical fence. Once the fence is constructed, the optimal model is selected from amongst those within the fence according to a criterion that can be made flexible. So you say, what is this all about? Well, let me give you a simple example to illustrate the idea of the fence. Let's say we are dealing with a regression variable selection problem. Okay, so if someone tells you, okay, I got 1,000 potential variables from which I want to select a best subset of variables. Okay, this is a typical regression variable selection problem. Okay, so then another person says, well, here I found two models. Okay, one model has 3 variables. Okay, the other one has 100 variables. Okay, now these two models perform almost the same in terms of model fitting. Okay, so you say, well, how do you measure model fitting? Well, you could look at the residual sum of squares. Okay, after fitting each model, you look at their residual sum of squares and find that these two models perform almost the same with the larger model, the one with 100 variables doing slightly better, okay, in terms of model fitting. So then the question is, which model is better? Okay? You know, the model with 100 variables isn't necessarily better, even though it fits slightly better, right? Because there's some other criteria that people would like to take into account. Okay? So now, if you construct a statistical fence, then it is possible that both models will fall into the fence. Okay? So then the question is, which model are you going to select? Okay? So this is the next step of the fence method. So from the models within the fence, okay, once the fence is constructed, you're going to select an optimal model from those models within the fence. Okay? And that selection criterion can be made flexible. Okay? For example, one of the criteria that is often used is the minimum dimension criterion. Okay? Basically, you select the model that has the smallest number of variables. Okay? So you can say the minimum dimension of the model. In this case, the model with 3 variables is preferred to the model with 100 variables because of its simplicity. Okay? Both models in the fence, but the model with 3 variables is much simpler. Okay? So here, your criterion of optimality is minimum dimension. But you can change that to something else that incorporate with your practical interest. Okay? For example, you may say, okay, here I got a model involves a variable that is not easy to measure. Okay? But there's another model which does not involve that variable. Okay? Both models in the fence. Okay? Now, personally, I prefer the model without using that variable because this will perhaps more cost effect. Okay? Because it doesn't involve the variable that is not easy to obtain information from. Okay, so that's just an example. You have this flexibility as another advantage of the fence. Okay, so now here's a little technical description about how to construct a statistical fence. So basically, we're looking at this inequality. On the left-hand side, is a difference between Q hat M and a Q hat M tilde. So what are these things? Well, Q hat M is a measure of lack of fit. Okay, for example, you may think of of the residual sum of squares in the regression setting. Okay, so think about the regression sum of squares. That's a measure of lack of fit. Okay, so this is the QM, but this can be general. It can be more general than residual sum of squares. Now, what about this term? This is the baseline measure. Okay, basically, this is the smallest residual sum of squares. You can think of it that way, but it doesn't have to be the residual sum of squares. For example, if you have, going back to that example that I gave earlier, that involves 1,000 variables. Okay, if you fit a regression that involves all the variables, you will get the smallest residual sum of squares, and that will be the baseline. So this guy is the baseline measure. Okay, so what? On the right-hand side, you have a constant C that is considered as a cutoff. Okay, so basically, this inequality is saying that I want my measure of lack of fit to be good enough in the sense that it is close enough to the baseline measure. Okay, so as long as this model fits good enough, meaning that it's within a striking distance from the baseline measure, I consider that model as being in the fence. Okay, so this is what we call the fence inequality. So then you say, how do you determine this cutoff? Okay, it seems to me that this cutoff is very important because it determines who's in the fence and who's not. Okay, so it's like a life and death. So how do you determine the cutoff between life and death? Well, there's some procedure to select this constant adaptively, which I'll illustrate with a little plot in my next slides. So this constant C can be determined, can be chosen either as a fixed or adaptively. Now this illustrates our simulations results show that the adaptive method, when you choose this cutoff adaptively, the finite sample performance can be significantly improved. Here's a little illustration on how you select how you would select the cutoff adaptively. So basically, you let the data tell you what is the best cutoff. Then you say, how am I going to do this? And how can I make the data speak? Well, here's the idea. This is the plot that shows the empirical probability of the most frequently selected model when you have different cutoffs. Okay, so what you do, you change this, you consider different cutoffs, and at each cutoff, you can calculate the empirical probability of the most frequently selected model. Okay, this is the model that is most supported by the data, but it changes with the cutoff. Okay, so somewhere in the middle, there is a peak. There's a highest point, there's a cutoff that corresponds to the highest empirical probability, and this is the adaptive choice. Is our choice of the cutoff, which we call adaptive choice of the constant C. So this plot is quite typical. It's usually a W-shaped. Okay, so you may wonder, you can tell that when the cutoff is 0, the highest empirical probability is equal to 1, and also when this cutoff is very large, the empirical probability is also very close to 1.